Hello and welcome to this series of presentations about the Dark Side of Git, where we explore some of the more advanced concepts of this version control tool. First off, I want to ask you if you ever had trouble with Git. I know in the past when starting out with Git I made quite a few mistakes. Quite a few times I was forced to copy my changed files to a different location because when I pulled my changes from Git, I had conflicts in the files which I did not touch. After checking out the branch again, I copied my changes back and was able to commit and push. Back then, I didn't understand how this could happen, but once I learned the more, let's say, occult features of Git, I figured out how that had happened. It was probably a forced push after a rebase or a cherry pick. Also, in my experience and maybe in yours too, lots of people do not know how to use a branching model properly. They often go their own way and just as often they fail. My name is Paul Negoescu and I want to explore together with you in this series the concepts of resetting and reverting, rebasing and squashing commits, cherry picking, branching models, and a few others. But first off, I have to let you know that this is not a presentation for beginners. I do expect some prior Git experience, but we will recap some of the concepts. Still, many of the concepts will go right over your head if you never worked with Git. And the second disclaimer is that a lot of the information is simplified and abridged. I've done this in order to keep things as simple as possible and the visual representations clear. Let's start with a short recap. Git, as we've already said, is a version control tool. It's the main tool enabling our successful collaboration when writing code. It saves us from madness when reconciling changes from our entire team, and it gives us the confidence of trying anything without being afraid of messing up the codebase. Some of the important concepts we need to already be familiar with are the staging area, also known as index, the working directory, the repository, what the commit is, what the branch is, and what the remote is. The main thing to understand when considering these concepts is how the files are treated. We are going to start out with a command line that we can see on the left and the representation of our files on the right. In our example, we have only our working directory, which is a local directory on our hard drive. We also have a README markdown file inside of it, but we do not use Git yet. To start using Git in our existing file structure, we are going to execute our first Git command called init. It literally initializes a new repository. The repository is found in the .git folder that now appears on your hard drive. As a bonus, we also get a special zone called the staging area that will hold the files we want to create a new version of. The concept of a staging area comes from shipping, and is the place where you would assemble all the parts you need to ship before actually loading them up and shipping them out. But the repository and the staging area are currently empty. Let's fix that quickly. We run the git add command, which copies the readme file to the staging area. It is now tracked by Git, which means Git is aware when there are changes in this file. We can now create a first version of our project by running git commit. This will again copy our readme file, this time to the local repository. And yes, I did not make a mistake, the file is actually copied from the staging area, not moved. This is one of the simplifications we've talked about. A few other simplifications we've already seen are with regard to the commands we ran. We didn't specify the required argument to the add command, and we didn't specify a commit message. This is where your previous experience should kick in and fill in the blanks. Moving on, we would now like to collaborate with our colleagues. This is usually done by using a central server that will be our single source of truth. Everybody pushes their changes to this place, and we all pull the latest changes from there. This central server is called an origin. Of course, we have to keep in mind that Git is a distributed version control system, which, in an overly simplistic way, means it supports multiple remote repositories and everyone who has a copy of the repository has a full copy of it, with all the files and versions. In practice, most often we will have only one remote, our single source of truth. There are always exceptions to this. Know just that having multiple remotes adds only a little bit of complexity into the fold. The concepts we discuss stay the same. Once we have our remote added, we can push to it, thus copying our files from our local to the remote repository. Please note that in our simplified view we have not specified all arguments for the git remote add command, and we did not specify the remote repository and the remote branch for the push command. We are going to assume these are also part of your pre-existing knowledge. We've seen all our basic commands. We've seen how files are copied around, but in practice this is not obvious and there is no easy way to observe all of this. The type of graphic representation we are most familiar with is the Git log of commits, where we can see in the form of a marble diagram all the commits we've made and all the branches we have created. But just what are these branches? We change our representation at least partially. On the right hand side we are going to see our Git log, our nice marble diagram, but it only gets built if we run our trusty git commit command. One commit creates one of these disks in our diagram. On the left hand side of it we can see part of the hash, which is sort of like the name of the commit, its unique identifier. On the right hand side we see two English terms, main, which is the name of the current branch, and head, which is a special label. We can easily see that main points to the current commit and head points to main. Once we commit again, we can see how the label main moves to the latest commit and head just keeps pointing at it. If our head is pointed at a branch when we commit, the tip of the branch, or the label, main in our case, always moves to this new commit. But what if we have two branches? By running git branch with the name parameter, we create a new branch. We called ours develop. Notice how our head is still pointed to main. If we were to commit now, the label main would move to the new commit. We would like the label develop to move and main to stay put, so we will switch to develop. When running switch, we moved our head and we are now looking at the develop branch. After running a couple of commits, we can see that the develop branch moved to the latest commit. Our history at this point is still linear. There is a straight path with no ramifications that we can follow from the tip of the develop branch to the tip of the main branch. You might be asking yourselves now, what is he talking about? Branches, develop and main are clearly on the same branch. Fair enough. Right now, it looks like both labels are on the same branch. But this is not actually true. In Git, a branch is just that, a label that points to a certain commit. The graph starts looking like separate branches only if we start making commits on the main branch as well, or if we get our changes from somewhere else. First, we switch back to main, and we are going to pull some changes from our remote repository where our imaginary coworkers have already pushed 2 new commits. It's difficult times for programmers, this pandemic. Some of us need imaginary coworkers when working from home. It's our coping mechanism. Once pull is done, we can see that our graph now actually resembles a tree with branches. This situation is a very common one. We have changes on the branch, we have changes on the other, and we want to bring the two together. So the next topic we want to cover is merging. This one is mostly straightforward. Note how our head is still pointed to main, thus, to merge some other changes into main, we run git merge and specify what to merge into main. Once merge is done, we should end up with a new commit, a special one that has 2 parents and incorporates changes from both. Remember how we had a graph that actually looked like a tree with branches? This is called a diverging tree. In these situations, a merge commit is created. Merging can of course cause conflicts if changes on both branches occur in about the same files and the same place in the files. Thankfully, these conflicts must be solved only once, as opposed to when we rebase, which is something we'll see in a future episode. Right now, our main branch has all the changes from all the imaginary colleagues, but we would not want to give up on the develop branch. We want all the changes to be in that one as well. So first off, we switch to it. Once there, we again run our trusty merge command, this time specifying main as the source. This, on the other hand, happens differently than we've seen before. Our develop label just moves up to the latest commit. But why is that? Well, the second time around, the latest commit, the merge commit, had a common history with the develop branch. See how that arrow from the latest commit points directly to the commit that was our develop branch before? This means we can get to it without going through any fork in our graph, against the tips of the arrows, directly. When we can do this, the merge commit is not necessary. We have a common history. In this situation, the moving of the develop branch to the latest commit is called a fast forward. It's hopefully obvious how fast forward can never result in a conflict. We just move a label around, that's it. We can even force a fast forward to be used when merging by specifying the ff-only flag. Of course, if a fast forward is not possible, we will see an error. Or we can force a merge commit to appear to mark the momentous occasion, one branch caught up with the other branch. I really don't think this is such a crucial piece of information in the history of a codebase, so I've never actually used this feature. You are probably thinking now, okay, We've seen how to merge two local branches, but I've actually seen a lot more conflicts when pulling. But your pull command just now did not end up in a merge commit. Why is that? Pulling can indeed end in a merge conflict or in a merge commit. It can also end in a fast forward. In our previous example, when pulling the 2 extra commits on the main branch, we actually ended in a fast forward. But what if we continued to work on the main branch instead, and now we want to pull? Pull is actually made up of 2 other Git commands. The first is git fetch, which brings in the remote branch. It copies the branch from the remote locally and names it with the prefix origin/. Obviously, if your remote is named Alex, your branch will be named with a prefix of Alex/. The second part of pull is a git merge. Pull runs a merge between the current local branch and the remote branch, and as we've seen previously, the merge will end in a merge commit. The graph looks exactly the same as it did previously, only our other branch is not named develop, but origin/main. Does it make sense? I think this is a good time to end our first episode. We've explored a lot of the basics of Git, like initializing a new repository, adding a remote, tracking files, committing them, how we work with branches, what a merge is, the 2 other commands pull is actually made of, and we've even seen how our files get copied from one place to another. This has been Paul, and I hope you enjoyed this introduction. If you did, please leave a like and return for the next episode in the series, where we start exploring history manipulation. See you there!